This is the second part of our discussion on the derivatives of complex valued functions. In the previous discussion, we defined what is the derivative of a complex valued function. We also solved some examples, and we decided that we are going to see similarities and dissimilarities between the real case and the complex case, because we defined the derivative in exactly the same way as we defined it for the real valued functions. And now our aim is to see at each and every step what are the things which are similar between the derivatives of real valued functions and derivatives of complex valued functions. So let's get started with our discussion. So recall that we defined the derivative of a complex valued function in the following way. We have two equivalent definitions, and it depends on the situation. We can choose any of these two definitions. So we are going to consider this simple example of where the function f of z is equal to square of this z mod. So in particular, we have z is equal to x plus iota y. Then f of z becomes f of x plus iota y, which is equal to mod of x plus iota y square. Okay, so and we know that what is modulus? It is the square root of x square plus y square, and if we take square, then it becomes x square plus y square. And we can easily see that it's a real valued function. Okay, so here f of z is real valued function. So what are we really calculating in this case? So given a point z is equal to x plus iota y, we are taking its distance from the origin, in other words the modulus, and we are then squaring it. So in particular, we can say that if we are taking the numbers which are equidistant from the origin, then for all of these numbers, the functional value of this function is going to be the same. Okay. Another observation which is going to help us in calculating or checking the differentiability of this function is the following interpretation of the function. Now this is equal to mod of z square. Now we can easily prove that it is in fact equal to the product of z with its conjugate. Now let's start checking the differentiability of this function. Now we are going to use this definition of the derivative, where we are calculating the limit delta z approaches to 0 of f of z plus delta z minus f of z over delta z. Now in this case, it becomes f prime of z is equal to limit delta z approaches to 0 and f of z plus delta z. So it becomes mod of z plus delta z square, but we also know that this is equal to the product of z with its conjugate. So, and we are going to use this interpretation. So in this case, it becomes z plus delta z multiplied by z plus delta z conjugate minus, once again using the same definition, it is equal to z into z conjugate divided by delta z. Now this is going to be equal to limit delta z approaches to 0. Now the conjugate can be distributed onto its terms. So z plus delta z, z conjugate plus delta z conjugate minus z into z conjugate divided by delta z. Now we can just multiply the terms and let's see what we will get. Delta z approaches to 0, z into z conjugate plus z into delta z conjugate plus z conjugate into delta z and plus delta z into delta z conjugate minus z into z conjugate divided by delta z. Now let's see what are the terms which will cancel out. So this will cancel out with this thing, okay, and nothing else will cancel out so far. Okay, so now let's see what is the next step. So z into delta z conjugate divided by delta z plus, and in this case delta z will cancel out with delta z, so we will only get delta z. Okay, so say in this case this will cancel out this case, so we have this z conjugate only, and plus in this case once again delta z will cancel out with delta z, and we will only get delta z conjugate. Now here is the last output that we get. Now we really want to calculate the limit of this function when delta z approaches to 0. So in this case we follow the same strategy as we discussed in our previous discussion. So if we want to prove that limit does not exist, then we take two different paths, and if z approaches to z0 along two different paths and the value of the limit is different along two different paths, then the limit does not exist. So here in the first step we choose the path in which z moves parallel to x-axis. Okay, so let's say this is the point z, and let's say if this is equal to x0 plus iota y0, then we are choosing the following path. So the path where z moves parallel to x-axis, so in other words this is the line, and we are approaching to, of course, this point z. And in this case we can easily see that if we take z to be equal to x plus iota y, then in this case this y, the imaginary part, is always going to be fixed, because this point is y0, so this is always going to be fixed. Now the observation that we are going to use in our further discussion is that whenever we calculate delta z, okay, so since we are moving along the path which is parallel to x-axis, so the imaginary part is always going to be the same. So whenever we calculate this delta z, the imaginary parts will cancel out each other, and we always get real value of this delta z. Okay, so this delta z is always going to be a real number when we move along this line. So in particular, so in this case x plus iota y naught minus x naught plus iota y naught, and in this case we can easily see that this is x minus x naught, which is real. So the observation which is going to be helpful for us, so in this case delta z is real. So if we have a real number, then the conjugate of that number is basically equal to itself. Now let's use this fact to calculate the limit of our function. Now remember that we want to calculate the limit of the function as delta z approaches to 0, and the function is z plus z conjugate plus delta z conjugate plus z into delta z conjugate over delta z. Now what are we going to use? Okay, so in this case delta z conjugate is equal to delta z. So this limit becomes limit delta z approaches to 0 z conjugate, so plus delta z plus z into delta z over delta z. So once again delta z is approaching to 0 and is not in fact equal to 0, so that's why we can cancel out delta z with delta z. So in other words they will cancel out, and let's see what is the output, plus delta z plus z. Now this expression is basically a polynomial in delta z, so that's why and we know that polynomials are continuous function, so the limiting value of this function is going to be equal to its functional value. So in other words we just take delta z to be equal to 0, and the output is going to be equal to z conjugate plus z. So this is the first path, which is the path when we move parallel to x-axis. Now let's consider this second path. So in this case we are approaching this z, which is equal to x naught plus iota y naught along the path which is parallel to y-axis. So in other words we are moving along this line, and of course on this line the real part is basically fixed, and if we take any number which is equal to x plus iota y naught y, then in this case, this x part, this real part of this complex number is always going to be fixed. So it is basically x naught plus iota y naught. And in this case, if we calculate what is delta z, which is z minus, let's say this is z naught. So this is going to be equal to x naught plus iota y minus x naught plus iota y naught. So x naught will cancel out with x naught. So this will cancel out with this. And what we are left with is basically iota y minus y naught. So delta z in this case is going to be pure imaginary number with no real part. And in this case, the following observation is going to help us. So if delta z is pure imaginary, then its conjugate is going to be equal to minus delta z. Now this observation is going to help us in calculating the limit when we are moving along the path parallel to y-axis. Now let's see how to calculate this limit in this case. So in this case, we want to calculate the limit delta z approaches to 0, z conjugate plus delta z conjugate plus z delta z conjugate over delta z. Now in this case, once again, this case, delta z conjugate is in fact minus delta z. So the value of the limit becomes the following. Delta z approaches to 0. So z conjugate minus, because it is delta z conjugate, it is minus delta z plus z minus delta z divided by delta z. Now in this case, we can see that this delta z will cancel out with delta z, and what we are left with is basically the following expression. Delta z approaches to 0, z conjugate minus delta z minus z. So once again, this is basically a polynomial in delta z, and so that's why its limiting value is equal to the functional value. So the value of the limit becomes the following: z conjugate minus z. So let's see what is our output. Now let's see what are our limits along path 1 and along path 2. So along path 1, we have which is basically parallel to x-axis, the value of the limit delta z approaches to 0. Okay, so when we calculated that limit, f of z plus delta z minus f of z divided by delta z is in fact equal to z plus z conjugate. Okay, so this was parallel to x-axis. So what will happen if we move along path 2? So path 2 is basically parallel to y-axis. Parallel to y-axis. What is the value of the limit? So limit delta z approaches to 0, f of z plus delta z minus f of z divided by delta z is in fact equal to z conjugate minus z. Now if we want that function is differentiable, then both these values must be equal. So this implies z plus z conjugate must be equal to z conjugate minus z. So this implies z is equal to 0. So in other words, every complex number of the complex plane fails to be differentiable apart from the point z is equal to 0. But this does not mean that function is differentiable at z is equal to 0. Well, if you want to prove that it is differentiable at z is equal to 0, then you have to do a separate calculation, which we are going to do in our next step. But over here, what we have proved so far is the function is not differentiable at any point apart from 0, because these two limiting values along path 1 and along path 2, they cannot be equal for numbers other than 0. So it is not differentiable for every point apart from 0. And if we want to in fact prove that, okay, so our doubt or intuition says that it might be differentiable at point z is equal to 0. So for that we have to start our separate calculations, and we have to take z is equal to 0, and if z is equal to 0, then we can easily see that this is limit delta z approaches to 0, f of 0 plus delta z minus f of 0 over delta z. So in this case it becomes limit delta z approaches to 0, so delta z into delta z conjugate, as we have discussed, and okay, so f of 0 is 0 divided by delta z. So in this case it becomes the following: delta z approaches to 0 delta z conjugate, and from here we can easily see that the derivatives exist because the limit exists, and it is in fact equal to 0. So the function is differentiable at z is equal to 0, and in fact the derivative is equal to 0. So what we have learned from this example, so the first thing which is very important is this is a real valued function. So in other words, f of z, which is equal to x plus iota y, is in fact equal to x square plus y square. So it is a real valued function, and if we consider its imaginary part, of course it is going to be equal to 0. And real part, if we take this to be u of x y is equal to x square plus y square, then as a function from R2 to R, okay, so here u is a function from R2 to R, it is a differentiable function because it's a polynomial in two variables. Similarly, this function v of x y, which is equal to 0, and of course it's a function from R2 to R, it is also differentiable. Now both these functions are differentiable, but this function f of z is not differentiable as a complex valued function because the input is a complex number. Now here let me roughly tell you what is really happening here. So sometimes we say that okay, this x plus iota y is really a point in the plane, and a point in the plane can also be written as the ordered pair x y, and in that case we can roughly, which is basically a mistake, which that's exactly I'm going to prove that it's a mistake. So we sometimes say that okay, roughly this function is a function of two variable and the output is going to be x square plus y square. And if I consider this f to be a function from R2 to R, then this is differentiable. But as a function of a complex number, it is not differentiable apart from the point z is equal to 0. It's a very important difference between the differentiability of complex valued functions of complex variable and real valued functions of real variables or Euclidean spaces like R2 and R3. Okay, so this is the first observation. The second observation is we have proved that this function is basically a continuous function. So f of z is continuous, but f of z is not differentiable. Not differentiable. So it is very parallel to our observation for real valued function. A function might be continuous, but it may or may not be differentiable at that point. So it is very parallel to that observation. And the converse part is it true, as in the case of real case, is it true that differentiability implies continuity? And in this case, it is also true that differentiability implies continuity. So for that, we have the following result. If we have a differentiable function, then the function is also continuous at the point. So what is given? So the given part is function is differentiable. In other words, we have the following limit which exists. The limit z approaches to z naught, f of z minus f of z naught divided by z over z naught. This limit exists. Now what do we want to show? We want to show that the function f of z is continuous at z is equal to z naught. So in other words, we want to show that if we calculate the limit of z approaches to z naught of this function f of z, then this is equal to f of z naught. So to show this thing, what do we do? So we start from the following expression. So limit z approaches to z naught, f of z minus f of z naught, which is equal to limit z approaches to z naught, f of z minus f of z naught. So we multiply and divide with z minus z naught, and we can do that because z minus z naught is basically a non-zero number. Now in the next step, we separate these two terms in the following way: f of z minus f of z naught divided by z minus z naught, and limit. Okay, so this is separate and this is separate. Limit z approaches to z naught of z minus z naught. Now when z approaches to z naught, and if we are calculating the limit of z minus z naught, then this is basically 0. And this expression is basically the derivative, which is going to be a number, complex number in this case. So multiplied with this number, which is going to be 0 in this case. So this is 0. So multiplied with 0. So the answer is 0. And if this limit is equal to 0, then this implies that limit z approaches to z naught of f of z is equal to f of z naught, and hence the function is continuous in this case. So in this discussion, we solved an example and we tried to figure out the difference between the differentiability of real valued functions and the differentiability in the complex case. And we also observed the relation between the continuity and differentiability in the complex case, and it turns out that it's exactly the same relation as we have for the real valued case. So in the real case, we also have every differentiable function is continuous, and the converse is not true. A function might be continuous at a point, but it may or may not be differentiable at that point. And it's exactly the same observation for the complex case as well. This is the end of this discussion, but we will continue discussing different properties of derivatives of complex valued function in our further discussions.